So our speaker today is Audun Myers from the Pacific Northwest Laboratory. And he's going to be telling us about data analysis using Zigzag persistence. Over to you.
Thank you. And thank you for the invitation to speak here today and for everyone being here. So first, very quick introduction to myself. So I have a background in mechanical engineering and then focus on topology and data science, and which I've taken now to the National Laboratory. So I want to start with some of the background of what the lab's interested in networks and computational topology. And working from the ground up. So to start, we have interest in graphs and network science. So just, two-way connections between entities, and all this falls under the field of network science. But then we want to go up a little bit further from there and look at two-way interactions. So instead of just these, or more than two-way interactions. So these are known as hypergraphs. So here you can see you could have a three-way interaction or an hyper edge that's just a single node. Another way of representing these multi-way interactions is through abstract simplicial complexes, where we include the support edges, and this all falls under the field of hypernetwork science. And then we could go a little bit further than this and use a specific tool called topology and study these spaces of abstract simplicial complexes, hypergraphs, and graphs using tools like persistent homology from the field of topological data analysis. And then one last step, which is really more the analysis side, is applying other methods like machine learning tools or sheaves or visualizations to understand those topological spaces. And this all falls under the computational topology side of research. So this really shows the entire structure of the lab's interest in networks and computational topology. So I want to start back one step to talk about the data and what type of data we might be interested in. So we're interested in a very wide range of data. It can range from vectors such as point cloud data, where here we have, when I say point cloud data, I'm talking about vectors in some space, which here there's a cat. So it's a point cloud data in the shape of a cat. We could have things like images, where you can also think about these as high dimensional vectors, right? If you wanted to flatten that to a high dimensional space. And really all of these different data sources, such as functions, images, audio, can all be represented as these high dimensional vectors. But one thing that just looking at data in this sense is missing out is the temporal aspect, right? And what I mean by that is, let's say this cat point cloud here is, instead of it just being a static cat, let's say it's moving and moving around. So those points, those vectors can be moving in time. Or instead of static images, we could have movies and seeing how those change over time. So that's really what I'm going to be talking about today and what I'm interested in. So a couple examples here, we could, and these are two from temporal data, or from cyber data, is a temporal flow graph or a temporal hypergraph, and where we could see certain types of activities, like here, when that blows up, that is called a ping sweep. So you can see that this data has both shape and dynamics. So I'm going to try to use tools to study not those individually, but together. So if I was to try to study them individually, I could use, let's say, topology to measure like a static representation of this data. Or I could use dynamical systems analysis tools where I could say, let's say, the number of edges or number of nodes over time and try to develop a model to predict that. But what I really want to do is combine these. So I can combine both dynamics and topology to get zigzag persistence. So that'll be the main point of this talk, is how can I actually use zigzag persistence to study this temporal data, and what sort of meaning can I get from that? So as an outline, I'm going to start with first describing what is topology. And then I'll follow into what is topological data analysis, how can we use tools from topology to study data. And I'll talk about more specifically hypergraphs and graphs, and temporal hypergraphs and graphs, and how they can be used to represent data. And then how we can apply zigzag persistence to study them. And then lastly, I'll go over several applications in this work. So what is topology? Topology you can think about as stretchy geometry here. So the classic example, donut versus a coffee cup. Are these the same or are they different? Well, from the standpoint of topology, they are the same. They both are one component and they both have a hole in them. But how can we quantify that more exactly? Well, to do that, we're going to use what are called Betty numbers. So Betty 0 is just the number of components, Betty 1 is the number of holes, and Betty 2 is the number of voids, and so forth. Where here in this coffee mug and the donut, we have a Betty 0 of 1 because it's both just one object. We have a Betty 1 of 1 because the handle, there's a hole in the handle and there's a hole in the center of the donut. And then we don't have any higher dimensional Betty numbers since there's no voids. They're both solid objects and we don't have anything beyond that. So how can we actually apply these Betty numbers to study the topology of actual data? Well, the main backbone of this is the field's topological data analysis. And there's a few different ways of going about it. The first main one is through level sets, where we can do things like pooling. You can think of this almost as the pooling of water for studying time series data, where you track when these pools of water start to form and when they overflow. You can do this similarly for images, where you study this is now the image as a surface, or even to higher dimensional objects. Alternatively, for point cloud data, which is a common focus, you can take these point clouds, cover it with spheres of a radius epsilon, and then create what's called the Vietoris-Rips complex. But all of these, the way we're going from data to something we study with topology is through what's called an abstract simplicial complex. So what exactly is an abstract simplicial complex and what makes it? So similar to like a geometric object, this is just a discrete version of it where we have points, edges, faces, and higher dimensional simplices. Where, for example, in these three different geometric realizations of abstract simplicial complexes here, where in the first one, A, we have points, which are just the black dots or nodes in a graph, edges connecting and then higher dimensional simplices. So we have a face here, and we actually, this is filled in between all these faces. So that would be a 3 simplex, versus in B, it's hollow there. So it would only have up to 2 simplices. So we can take these and study their shape using topology, using these Betty numbers again. So for in A, we have dimensions, we can look at the Betty numbers in dimensions 0 to 3, where we can see there's one component. There's one hole here. So we have a Betty 1 of 1, and then in B, and nothing higher. And then in B, we have those same, it's very similar, except for this is hollow here. So now we have a Betty 2 of 1. And then in C, we have 2 different components here. So it is a Betty 0 of 2. So this is how we can use Betty numbers to study these abstract simplicial complexes. But we still haven't answered the question, how can we actually use these to study real data? So let's look at just a simple toy example. Let's say I have this point cloud data, and it's just obviously a circle. Any of us can see that, we can look there, it's a circular shape, but I want to quantify that circular shape and measure that. Well, one way of doing that is using the Vietoris-Rips complex that I mentioned earlier. So we draw a sphere around each of these points of a certain radius, and then we construct the abstract simplicial complex from this. And this is based off of when these spheres intersect, you add an edge, 2 of them do, and then if 3 of them intersect, you add a face, and so forth. And then we can measure its shape using Betty numbers, right? So we have one component and one hole, which is great, right? Now we know this has a hole, right? Tells us it's general topology, but there's a couple difficult problems here. First, I don't know the size of the hole. You just chose a certain radius, and it really doesn't tell you anything about the geometry of this. Also, choosing that radius isn't very trivial, right? I chose a good one here, but that's because I made this and I chose exactly, and I knew I could visualize this data. But what about if it's in higher dimensions? You can't visualize it. It's a harder choice. So what you can do instead is you choose all of them. So what I mean by choosing all of them, I mean you scale up this the radius of these spheres and then create an abstract simplicial complex at each step. So I'll wait for this to rerun, but what you can see is H0 are your Betty 0 numbers and your H1 are your Betty 1s. And you can see that there's a bunch of components that are persisting until they combine. And what we're tracking is how those topological features persist. So you can see at around a radius of 0.5, this hole connected, and then it keeps going, and eventually it fills in. So that would be its depth. So we'd say that this is the birth and depth coordinates of a topological feature. The one thing that's kind of tricky with this, and this is called persistent homology, by the way, is that it requires that each abstract simplicial complex, the previous one is a subset of it. So we show that through these arrows here, and this might not always be the case, especially with temporal data. So we have the persistent homology case, right? So each abstract simplicial complex, the previous is a subset. But let's say we have an arbitrary case here where we have just a sequence of abstract simplicial complexes with no rules between them. We don't know if one is a subset or the other, or if neither of those cases. But we can force this to happen. And we do this by taking either unions or intersections. So for example, if I have abstract simplicial complex X1 and X2, I can take the union of X1 and X2, and then I know that X1 is a subset of that union and X2 is a subset of that union. Then I can move on to the next pair, X2 and X3, and do that same union. And so I have this back and forth subset directionality where I move my persistence direction is forward in the sequence though. So now the same that allows you to do persistent homology allows us to do this zigzagging of the persistence. So aptly named zigzag persistence, where again, we're going to get this barcode output, which tells us where topological features are born and where they die. But instead of it being some epsilon distance or some filtration, it's a filtration in time. So we're looking in time, when do these topological features appear, how long do they persist, and when do they die. So now we see that, let's actually go over a quick example of how this could be applied to a sequence of abstract simplicial complex. And what does it mean for these features to persist over time? So here I have a sequence of 5 abstract simplicial complexes at time 0, time 1, 2, 3, and 4. And I can take my unions, right? So you can see here the union of K0 and K1 is, I'm going to call it K01, and I'm going to take the average time between them, so time 0.5, and I get this abstract simplicial complex, and you can see both of these are subsets of that. So this is this zigzag behavior where we have these subsets up to the top. And at the very end, I'm going to add an empty. So it's just going to empty abstract simplicial complex. So everything will die at the end. So if I apply my persistence to this, and what I'm going to try to detect, one of the things I want to know is, right, there's this hole that shows up that starts at time 2 and it disappears at time 3. So that's one of the things I definitely want to be able to pick up using one of the features I might be interested in. So I can do this now, getting the zigzag persistence barcode. You can see that at time 0, I have 2 components, which are represented as these 2 bars starting at time 0. And then quickly at time 0.5, one of these barcodes ends, and that signifies that this is the joining of these 2 components. So this short line here represents that short lifetime of this single node component. And then as you persist through time, this one component stays and it continues. But then at time 2, we can see this hole shows up, and this is tracked in H1. So we can see that it shows up at time 2 in H1, keeps persisting through time 2.5, and then at time 3, it disappears. So these are really should be represented as half-closed intervals, but yeah. So you can then move forward and this same component is still persisting. And then finally at time 4, it breaks up into 2 components again. So you can see the second bar here shows up, and then everything disappears at time 4.5 because I go to the empty set. So how can we actually generate these simplicial complexes from data so we can apply this tool to study this changing topology? Well, my first work in this area was just applying this to networks and not hypernetworks. And this was work during my PhD with my advisor, Dr. Firas Kasana, and co-advisor, Dr. Elizabeth Mudge, and David Mills. So a graph, probably don't need to describe this to everyone here, but this is just where we have vertices that are connected in a two uniform way where we have, which we call edges. So we can have edges relating to vertices. And we can apply this zigzag persistence pipeline to these by taking what is called a temporal graph, where each of these edges, let's say here's my static representation of the graph, has a time attribute to it. So for example, the edge 0, 1, so this edge from node 0 to node 1 is active from about time 0 to time 2, and then about time 4 to time 8. So these show when is this edge active. And if I do a sliding window procedure here, I can get snapshots of this temporal graph and then take their unions between them. So now I have the sequence of temporal graphs or sequence of graph snapshots, and then I can get just the direct abstract simplicial complex representation of these, where nodes go to 0 simplices and edges go to 1 simplices. And then now I have the correct sequence of simplicial complexes to apply zigzag persistence. So let's see a little bit more detail how this is done. So here's that same graph, right? And each of these edges, just like before, has a time that it's active. And then I can get a sequence of graphs from these sliding windows here. So these different color coding are the different windows. So this first window is from time 0 to time 1. And you can see the only edge that's active during this time is edge 0, 1. So I just get this simple graph here. And then at the next window, get graph 1, which has edge 3, 4 and edge 0, 1 active. So I get this graph and so forth. And I also can take unions of these two windows to get a graph where I get, in this case, it's also 0, 1 and edge 3, 4 during this larger window. If I apply this along the entire length of the data, I can get, and then I get my sequence here and I create abstract simplicial complexes from them. And then I get my, what's called here is a persistence diagram representation of those barcodes. I can capture these topological features. So for example, in H1 here, I have this hole that shows up at graph 3, 4, and then dies at graph 4, which is represented that persistence pair there. And then I have a second hole that shows up at graph 5, 6, and then persists until graph 8. You can see it's captured by that persistence pair there. So now let's look at some actual applications of how we apply these the zigzag persistence of temporal graphs. So the first application I looked at was temporal transportation networks. So this is in Great Britain, where we have air, coach, and rail travel. I'm going to show you one quick example of this and focus on rail network. So to kind of visualize this, here's a GIF of how we constructed this network. And each node is a rail station, and each edge is only active when there is a train on that rail between those two stations. And so I want to know are there any periodic behaviors between each day of the week? Is there a difference when I get to the weekend? And what we found is we can visualize these changes fairly well through the H1 or the holes that are in this graph over time through zigzag persistence, where we can see these daily trends during the work week that are very similar, right? So these first 5 are almost identical trends. But then as we get to the weekend, the topology of this transportation network slightly changes during the weekend. Definitely great to do more research in here and trying to automate this change detection, but this was a great first use case of showing, wow, okay, so we can actually see these trends here in the topology and how how is it changing throughout the week. In this work, we also looked at an application to a dynamical system, a simulated one. So to do this, we needed to first create a network from time series data. And the way we did that is through what's called an ordinal partition network. So here I have time series data where I have 3 points sliding along this time series. And what I want to track is the shape of these 3 points, or the permutation of them. And the permutation can follow, because there's only 6 different possible patterns. And you can see as the changes, you can track them. So pi1 here is where they're all increasing. You see this will happen right as this goes up. So it goes to pi1 there. And now if I track these over time, I get this permutation sequence here. And I can treat each permutation as an edge in a graph, and then add an edge between nodes if there's a transition between them. So there's a transition from pi6 to pi4, so I add that edge. So now what I can do is I can go to higher dimensions than just 3 points. I can do, let's say, 6 points, and then there's 6 factorial different possible permutations. You get a much more complex graph that really captures the dynamics. So we use this to study what's called intermittency, and we use this specifically in the Lorentz dynamical system as a test case. And what the goal of the intermittency problem is, you have a time series data that transitions from chaotic dynamics to periodic dynamics. And what you want to do is automate that detection of those changes. So you can see here in red here is a section of chaotic dynamics, while in blue over here is periodic dynamics. So we can construct these ordinal partition networks at each window. We can do this a sliding window across the whole time series, and then we can create apply our zigzag persistence to all of these windowed ordinal partition networks, and we get this persistence diagram, where I want to quickly explain what these points in the persistence diagram mean, where we have this chaotic region shows up as a cluster of cycles H1 right here near the diagonal, which means it's all really short-lived cycles. So you can picture this network and as it temporally changes, as quickly these cycles show up, and they're short-lived and disappear very quickly. While in a periodic region, which is represented at this point here in the persistence diagram, is a cycle like this that just keeps persisting in time as this window slides along it. So you can interpret this persistence diagram as all of these off diagonal points are the ranges in which there is periodic dynamics, while these clusters near the diagonal are where there is chaotic dynamics. So now I'm going to...
Can I ask a question? So
yeah.
Maybe I missed it, but so what is the data you're using here in this? Do you take some tokens embedding of this time series, or?
So it's not the tokens embedding. So it's simulated Lorentz dynamical system. So just the x sub t variable here. And I'm not doing I'm doing this, I'm constructing the ordinal partition network. So it's kind of similar to tokens embedding, right? Because you have this equally spaced point that would normally embed it into 3 dimensions, but instead of embedding it into 3-dimensional space, I'm embedding it into this, each vector into a node into this graph called an ordinal partition network. So you can see like, and you can even think about it in the tokens embedding space as splitting up that space into different regions, where each region is represented as one of these permutations. But yeah, so think about it, instead of tokens embedding, it's embedding it into a graph, and then embedding it into a bunch of different graphs here, and then getting that zigzag persistence to study how it's changing.
Okay, all right, thanks.
Yeah.
Thanks for the question. Quick question as well. What n are you using then? Is that n equals 6, like the length of the permutation?
Yep, this is n equals 6. Yep.
Okay, cool.
And quick note on that, n equals 6. There's I had some other research where we looked at what dimension, what is a good value of n for studying time series data like this. it turns out that n equals 6 is a great answer no matter what. It's not like you don't get any benefit after like using n equals 10. It's actually just gets computationally more difficult and more cumbersome, so it doesn't make sense to go really beyond n equals 6. So next application is social network analysis, and for here we're going to move into the hypergraph. So this work is with several PNNL co-authors, Cliff Jocelyn, Bill Kay, Emily Purvine, Greg Roque, and Madeline Shapiro. So a hypergraph, I mentioned this earlier, but I'll say it again.
A quick question in the chat
Yep.
before you want, if you like. It says, are there any similarities to wavelet analysis?
Yeah, definitely. You could use wavelet analysis on this problem for sure, right? So you could get these windows, and you could do get your Fourier spectrum on each of these windows, and you would probably see in your spectrogram these regions between periodic and chaotic dynamics. But what's really nice about this is, or zigzag persistence, instead of you just getting this Fourier spectrum at a specific window, it's actually relating windows to the next window. That's kind of the cool thing about zigzag persistence, is that it's relating all of these windows together, that there's all of these cycles and that they're the same cycle. So there's slight differences there, but yeah, you could use a spectrogram to do a similar analysis. It's a good question.
What software do you use to compute zigzag persistence?
It's called Dionysus 2. It's built in, it's a Python package. Although advertisement, we are working on our own zigzag persistence code at PNNL. So soon, hopefully, this will be publicly available. That code will be so.
All right.
Yeah, if interested, Dionysus can have some challenges getting it to work, depending on your operating system. All right, so yeah, hypergraphs for studying social networks and temporal hypergraphs. So I wanted to quickly go over what a hypergraph is again. So like a graph, you can have vertices. So in this example over here on the right, this is Les Mis hypergraph, where vertices are just your characters, and let's say your hyper edges are the different scenes. So you could say a scene connects there's 9 different characters here. So one scene is 9 characters versus another scene might just be between 2 characters, which is that hyper edge. And let's say because these are scenes, they have some sort of temporal attribute to them, right? The scene happens at time 1, and then the scene happens at time 2. So you could look at this sequence of temporal graphs and say, oh, at this point, let's say there's 2 components and 2 characters have never met before, but then it all merges into one graph, and you could say then those characters met. So it's a generalization of graphs, because we can now have these multi-way interactions between entities or vertices. So yeah, how can we apply zigzag persistence to study these? And we can do that in a fairly similar way we did to temporal graphs. So here I have, again, a temporal hypergraph where each edge has a time period of which it's active. And then I do, similar to graphs, a sliding window where I get these graph snapshots at each window, right? So if I looked at these 5 snapshots, they would show up here as this. And then I can get what's called the associated simplicial complex from each, which is just a hyperedge connecting, let's say, 3 edges here would just go to a face or a 2 simplex. So I'll go back and forth a couple times here. But you can see how it's quite simple to go from the hypergraph to the associated simplicial complex. And now that we have these associated simplicial complexes, we can apply our zigzag persistence pipeline, take the unions between them, and then get our zigzag persistence barcode. And this is the exact same one from the previous example. So again, there was a hole here, right? Persisted from time 5 to time 7. We had 2 components at the beginning through 2 barcodes. One persisted the whole time. So one component persisted the whole time, and then it split up at the end. So same as before. now let's see how we can actually apply this to social network data. So this is social network data from a problem shop called Social Network Problem Shop 2022. So this is right after COVID. So these are all these subreddits related to COVID for about 1 year worth of data. And so for the NCOV subreddit, we can create we represent each thread as a hyperedge, and then the authors in that thread as nodes. So here's an example hypergraph from a moment in time on day 25 for an hour worth of data, what this hypergraph looks like. And then so you can see that some of these threads last a long time, some of them are very short-lived, and then we can create hypergraph snapshots over time. Here we have like number of edges in the hypergraph, number of vertices in the hypergraph, and so forth. So what we want to do though is apply zigzag persistence, study how does the topology of the social network evolve. So here's some of those results. So we can see the barcode here where we have, let's first focus on H0, which shows that there's one conversation that really persists the entire time the subreddit was active. And we can also see that during certain points when in H1, when there was the sharp increases in popularity, there seems to be a correlation to holes in the hypergraph showing up. So for example, there's a hole there, but and they're all relatively short-lived. But as you can see, yeah, increases of popularity, more people jumping in and new connections being made, is creating these topological holes in the social network. We also did an experiment here looking at the difference. I've only talked about unions previously, but we also have intersections is another way of applying zigzag persistence. We found very little, there's still some difference, but both intersections and unions capture the main topological characteristics of the temporal hypergraph. So I'm going to move on to the next zigzag persistence application, which is some of the most recent work, which is in cyber data analysis. So as a general pipeline, and this is recently published work, malicious cyber activity detection using zigzag persistence, and lots of co-authors that I'm not going to read off all their names, but yeah, all PNNL employees. So what we start with is log data, which is it's network flow data. It's multi-column, and we can create hypergraphs from this data during like 10 minutes of data at a time or 5 minutes of data at a time. And then I can look at how does the topology of that hypergraph evolve over time using zigzag persistence. And then we do a vectorization of the barcodes to get vectors, which we feed into an autoencoder, and then to try to do anomaly detection. So and anomalies usually correspond to malicious activity occurring in network log data. So how are we actually creating these hypergraphs? Well, here's a very simplified, really small version of what this data might look like. So each row has a timestamp associated to it. And then what we're going to do is take the different combinations of, we choose two columns here. I use destination ports and image paths, or which you can think of as like executable files. And I create a hypergraph by looking at their pairs. So destination is a really basic one, but destination port 138 is paired with system, and then it's paired with system again. So it's just a single hyperedge of 138. It's paired with just system. Same for 5355 and SVC host, and 443 and Firefox executable. So you can see it's just a really simple hypergraph, but this is how it's formed. And when you use more data, they have more unique structure. So here's just, I took a couple of snapshots to show you kind of what the static representation of these looks like during benign and malicious activity. So during benign, it's usually pretty simple structure, usually just 2 or 3 nodes, and it's relatively static versus malicious. You have a little bit more structure, but these are actually topologically equivalent, right? They're both just 2 components. There's no holes there. But where the real difference comes in is in the dynamics. So if I look at 20 minutes of data here, the image path, you can see for the different image paths of executables, so many are being used in 20 minutes of data versus during benign activity, it's pretty, it's every minute or so, there's a different executable being used. So combining these using zigzag persistence is the next goal. But to really study that zigzag persistence barcode, we need to use an autoencoder. So the way we do that is we break the full zigzag persistence barcode into 1 hour subwindows, and then we vectorize those using what's called Adcock-Carlson coordinates, which are really just summary statistics of those persistence diagrams, which are then fed into an autoencoder. So the autoencoder takes this, because we're looking at both dimension 0 and dimension 1 topology. It's an 8-dimensional vector that is fed into this neural network that brings it down into code, or the latent space, which is a lower dimensional space, and then reconstructs it through a decoder back into that 8-dimensional space. And the goal of the autoencoder is it's typically used for compression. So what we want is for the input and output to be the same, or as close to the same as possible. So that we can do a compressed version of that data. But you can also use them for anomaly detection by saying, all right, for most of the data, I can, for what I know is benign data, I can have it input, and I can train an autoencoder on that, which does a great job, right? So normal behavior, it can reconstruct it, and I have a really low loss between output and input because they're similar. But then if I test it on malicious activity, what I would hope is that it does a really bad job of reconstructing the output so that it's similar to the input. So then you get a high loss during malicious activity, or you would hope that. Another pipeline we want to look at, instead of as a point of comparison, instead of just zigzag persistence, it's just summary statistics on the hypergraph snapshot. So number of edges, number of vertices, components, and maximum diameter, things like that. And we again feed this into an autoencoder. So let's actually look at some of those results now. So we have benign barcode here, right? So the dynamics are really, really simple during benign activity for cyber data. So you can see it's just one main component that's persisting with a bunch of pretty even short intervals of components that show up and then disappear. And we get these loss values when we apply our autoencoder. So you can see, paying attention to scale, 0.001, very low loss for both the Adcock-Carlson coordinates and the hypergraph summary statistic autoencoders. But in comparison, for malicious activity, we get a much more interesting zigzag persistence barcode. We could see a lot of components showing up in different intervals of length that they persist, as well as some higher dimensional features, such as a one-dimensional hole here. And we also have these vertical red lines represent the specific attacks that were happening. So during this first group, we had PowerShell Empire, Mimikatz, and injection type attacks. And then the second one are more ping sweep and ARC scans, which are sending out a signal and then getting a response from people trying to find vulnerabilities in the network. So when we look at our autoencoder losses here, we do see a really sharp spike using the Adcock-Carlson coordinates, which is really good. So this tells us that the Adcock-Carlson coordinates are doing a great job at detecting this type of Mimikatz and injection type attacks for malicious activity, while it does not, however, pick up the ping sweep type activity. And this is based off of, we're hypothesizing this is because of the hypergraph construction that we're looking at doesn't pick up that type of attack very well. There might be other hypergraph constructions from this log data that would do better. We also have the hypergraph summary statistics results here. But you can see they do detect there is an increase during this malicious activity, but it's not nearly as pronounced and sharp. So it's not as clearly interpretable of exactly the time window that attack happened in, which is an important thing to be able to do. So as kind of a summary of these results, I'm gonna gloss over this table, but what we can look at is the median loss value for Edcott-Carlson coordinates between malicious and benign over all of the data. We got a ratio of 35.7 here, versus compared to the summary statistics, it's only 7.6. So this really tells us that the zigzag persistence method of studying this data is providing a much more clear distinction between malicious and benign activity, which is also a good thing. So the last application, which can go through pretty quickly, is through, it's a work called
We have a question in the chat here that just says,
Oh,
how are you going from the hypergraph to the simplicial complexes here? Perhaps they missed this.
Oh, yep. I'll have to jump back a little ways. So the way I was doing that was almost there. So here are the hypergraphs, some example hypergraphs, and I jumped to abstract simplicial complex by taking what's called the associated simplicial complex. So for example, here I have two edges and one 3-edge, but I just take so the 3-edge would break down to the face and all 3 edges and all 3 nodes there to get the abstract simplicial complex on this left side. But you have duplicates here through these two edges, so those just all fall into one simplex over here with the 3 edges, 3 nodes, and 1 face. You do similarly for this, like you have multiplicity of the same hyperedge, that's fine. It all just kind of falls down. You kind of collapse it to this simplicial complex.
I have a quick question actually. The data that you're using, this kind of simulated malicious data, or have you taken the data from somewhere?
That's a good question. Yep. So it's called OptC, the data set, and it's operationally transparent cyber data. It's real. It's somewhat simulated data. So they took a real network data, and they have what are called red team actors. So these are we have the ground truth data because it is a red team of cybersecurity experts who are trying to break into this system using intrusion type attacks. So they take logs of exactly what types of attacks they did at what time they did, so that you can go back and try to detect that and automate that detection method. So it's a fairly popular cybersecurity data set called OptC.
Nice.
Do you have some interpretation of the long H0 bar in the benign case that you showed? That what does it mean in this case?
Yeah, so that H0 is here is most likely due to standard activity. So if I go back to this example here, which not here, so destination, it's probably from the hyperedge, from some destination port hyperedge connected to system. So system is an executable that's called almost constantly. So there's going to be, it's almost always going to be there. So that's going to force that component to be there. Versus there might be background operations such as, 5355 and SVC host that only happen every 5 minutes, let's say. And that's what causes these short intervals. So it happens on constant intervals of every 5 minutes, versus when you have malicious activity, what you might have is some red team actor who is using uncommonly used destination ports or uncommonly used executables, and it's connecting lots of destination ports that aren't normally used, right? So it might be trying to take data from one part of the network and bring it to another part, and that's going to be connecting uncommonly used destination ports. They might be doing it in multiple ways. So what ends up happening is that the topology of these hypergraphs is changing significantly and at different time scales with these malicious activity.
Right.
Image classification. So this work was with Henrik Finge and Tegan Emerson, and it's called Top Fusion. So the main idea was to try to fuse multimodal data together. So here, one of the data sets we used, for example, is AVMNIST. So this is where we have images, hand-drawn images of numbers 1, 2 through 9, and we're trying to classify those, but they're also paired with audio data. So where someone is speaking the number 1. And we want to try to improve, this is just kind of like a toy example one. The actual applications are much more useful, but we want to try to fuse this data to improve my classification accuracy. So fusing different modes of data, such as images and time series data here, isn't a very trivial problem, but one way of doing it is using topology. So we did this through sublevel set persistence for when doing in the time series data, which we get these persistence diagrams, which then we vectorize into what are called persistence images. And then we can also do this on the images using sublevel set persistence, as well as what I'll be talking about, which is the zigzag persistence scanning of these images. But the main goal is we stack all of these images together then, these persistence images, and then we get this high dimensional image, which we can feed into a 2D CNN to do classification on. Yeah, so the image part of this, which I'm going to focus on, is a bunch of handwritten numbers, 60,000 training images, 10,000 testing images. But I want to show now, yeah, how can we use zigzag persistence to scan these? So we scan them by taking these, again, kind of a sliding window, both in the horizontal and vertical directions. And if this window falls over pixel values that are higher than a specific threshold, we can create a simplicial complex at that time. So you can see here these simplicial complexes. So if their pixels are neighbors, you add edges between them. And then you can then see how this picks up the persistence barcode in the bottom here, picks up the one component, splits to 2 components. So now there's 2 bars signing, and then they combine back to 1 component at the end here. So we can take these persistence barcodes and create persistence images from them, and then feed them into doing that fusion with all the other filtrations. And we were able to get up to 99.5% classification accuracy using this really simple, shallow 2D CNN, which is comparable to some of the state-of-the-art methods, which are using like deep neural networks to study these images directly. So it kind of shows the usefulness of zigzag persistence for studying images. And there was a significant, without using the zigzag persistence, I believe we were only getting around 96% classification accuracy, but by fusing in together the zigzag scanning, we really brought up that classification accuracy. So yeah, that's everything. I want to thank all my collaborators listed here. Yeah, and after this talk, feel free to contact me at my email here. But yeah, thank you all for listening. Are there questions?
Great, thank you. Shall we just thank the speaker quickly? If everyone wants to unmute or thank however you choose to thank, and clap.
Thank you.
And yeah, does anyone have any questions? You can either unmute yourself and ask, or post in the chat and I can read it out for you. So any questions?
Yeah, I have a question about on your images where you say you choose a certain threshold. On the MNIST dataset, that threshold's pretty obvious to choose. Have you ever considered cases where it's a less obvious threshold?
Yeah, we did some texture detection data set we looked at also. And yeah, it wasn't nearly as trivial of a choice. So what we did there was we also did this fusion, but just using the zigzag scanning, and we chose a bunch of different thresholds, all the way from the 0 all the way up to the maximum pixel value 255. So we are able to get these zigzag scans at different thresholds. So yeah, kind of did the classic topological data analysis approach of choosing all the values instead of just one. that's a good question. Yeah, not an easy choice.
When you use that method, did you eventually settle on a threshold that worked, or did you feed everything in?
Yeah, that's another good question. We did some experimentation there of what's important, like how many do you need? And so we looked at as many as like 100 different thresholds all the way down to one just at the middle, right, 125. And we found that using about 3 different thresholds worked. It was a nice trade-off between computation time and accuracy. So by 3, I mean, you could, let's say your pixel values are from 0 to 255. I think we chose values like 50, 125, and 200 around that area. So you can then you would pick up on different features at different thresholds without going overboard and calculating 100 different thresholds.
Oh, awesome. Thank you.
Yeah, thanks for the question.
Marco has a question, I think. Do you want to go ahead and ask?
Sorry, can you hear me?
Yep.
Oh, cool. I was just wondering, there's been some work like in the last few years on developing temporal link prediction algorithms. So just like, exactly what it sounds like, just the predicting edges on temporal graphs. And so I was just wondering if like, do you know, I currently work on them in Sandia National Labs, and we've been kind of exploring some topological things on there. And I was wondering if you have any applications to maybe using this zigzag persistence as maybe some ground truth, because like so a lot of these algorithms work with embedding nodes in high dimensional space, and so ideally if you're trying to recover these relationships, you want to preserve the topology, right? So like you don't want the embeddings of these nodes to violate the ground truth expectations of what the global structure is. So yeah, I was just wondering, have you seen any of that?
I haven't done any of using zigzag persistence with that link prediction stuff like that yet, but that's a great idea. I could definitely see it being done, right? Because thinking from a dynamical systems perspective, you have these barcodes. If your link prediction, right, if it's a possible one where it's predictable, then you should be able to model the dynamics through the zigzag persistence barcodes, and then that could help you do link prediction, right? Because like you're saying, the topology should be predictable, and you should. So yeah, I could definitely see that being done. I have not read any work on that or done any work in that area, but it seems like a great idea.
Yeah, I've been thinking about like maybe having something that adds like a bottleneck distance term to the loss function or something. I don't know, but I think it'd be interesting. This is fun. This is really good work. Thank you.
Thank you. Yeah.
I was wondering about the first stuff with the rail network. Did you look? Because you had the 2 other networks as well, the air network and the road network. Did you look at those 2 as well? And did you see similar results with those, or?
Yes, I did. Trying to pull it back up again. Yes, there was very similar results here with the. I remember the air network was more sparse, but there were still daily trends. They just weren't as clear as this daily trend. But yeah, there was definitely that you could use this to do like predictability through those networks.
I also had a combinatorial question for you about the permutation
Okay.
stuff.
Yeah.
So you make these graphs right from the signal data. Have you looked at the kind of graphs you can make? Because there's certain edges that just can't appear, I assume. Right? For example, you can't go from the increasing permutation directly to the decreasing permutation. So you can never get an edge between 1 and 6 here, for example. Have you looked at kind of what graphs can be made by these and different things, stuff like that?
That is a great question. And I've been asked that a couple times before, and I've always wanted to go in and look at that. But I just I've never found time to do that work. But it's a really good question. Like the space of graphs that the ordinal partition networks could exist on would be that'd be a really cool question. And really, yeah, what graphs could not exist?
Yeah, it looks like a fun problem. Maybe if I can
It
find some
does.
time, I might have a play with.
Yeah. And I mean, if you only looked at like, dimension 3, it should be, you might even be able to visualize, it might be combinatorially small enough to actually do.
Yeah.
Yeah, that's a good thought. Definitely need to jump back to that at some point.
Nikki says depends on the functions you allow.
I was just thinking for that question you were saying, if you have to oscillate really quick, I feel like you could kind of make the timing, if you just have like really fast things, you could get most of your graphs that you wouldn't if you have more constraints on functions and the spacing between your little sliding permutation.
And how much you move, right here, I'm only moving by one each one, but if you shift by more,
shift and your width of your setting, your permutations, all those. Yeah. Exciting though. Cool work. Thank you.
Yeah, thanks. Yeah. Yeah, I think you're right. I think you're right though. It might be that all graphs are possible if you change that so that you could shift if you shift by more than one. But if you only shift by one, then it is kind of different. Which I've looked at graphs where you can shift more, and it's kind of just empirical studies on what do those graphs look like so far.
Yeah.
Would it help to think about it as if you break up the state space into the little cross regions? Hi, Audun. The little cross where you're looking at the whatever it is, the hyperplanes x1, xi equal to xj situation, right? So like you could get any edge that you wanted to as long as you can make yourself go exactly through that center hyperdiagonal. But I'm guessing if as soon as you have some sort of noise or any sort of general position assumption, you'd have limitations.
Is that organization called something? Is there just a name for that kind of breakup of that space?
I don't know.
Okay, I'll dig. Thanks.
At some point, Audun made a really pretty, I don't know if you've got your GIF somewhere. I don't want to make you pull up the thing right now, but he has a really pretty GIF actually walking around in the hyperplane version of this in 3D.
Yeah, is that in one of our papers?
I think I am. If it's not one of our papers, it's in the depths of my computer. But yeah.
Yeah. I want to say it's in the topological data analysis for permutation parameter selection paper. I think there's a figure showing that hyperplanes there. That's a good point though, right? The hyperdiagonal where all those planes intersect, you should be able to transition from any permutation to any permutation based off of that. Yeah.
Are there any more questions?
I know you mentioned that P&L is working on the Python packages for zigzag persistence, but you said there was another one. What was the name of it again?
Dionysus 2, or just Dionysus. Yeah, it's a general topological data analysis package. So yeah, if you don't have a link to it, but yeah, like Google search Dionysus and topological data analysis, I'm sure it would come up.
Awesome, thank you.
Yeah. And a lot of the figures, the hypergraph figures were created through a Python package that Pacific Northwest supports called HyperNetworkX. So if you're ever interested in working with any hypergraph data, it's a good package to use.
Awesome, thank you.
Yeah.